The Lorentz Force is a phenomenon experienced by an electric current which is made up of negatively charged particles or electrons moving through a wire. Shown here as yellow particles, electrons move from negative to positive. However, the convention is to think of electrical current as moving from positive to negative, so that's how we'll show it here using red particles. If it's not moving, a charged particle doesn't create any magnetic field. But when it moves, it generates a little magnetic field around it, shown by these green arrows. Flip the direction of the current, and you flip the direction in which the magnetic field circles around it. The magnetic field produced by the current will interact with another magnetic field, just the way two magnets repel or attract each other. Here's a horseshoe magnet with a north and south pole. The magnetic field always points from north to south, as shown by the blue lines. This wire is arranged in a kind of pendulum, so it can swing back and forth. Let's insert the horseshoe magnet into the setup and see what happens when electricity runs through the wire and creates a magnetic field around it. The pendulum swings in a different direction perpendicular to the horseshoe magnet's field and to the movement of the current. If we reverse the direction of the current, the magnetic field it generates will turn in the opposite direction, causing, in turn, the pendulum to swing in the opposite direction. Flipping the horseshoe magnet around to reverse the magnetic field around the pendulum will also cause the wire to swing in the opposite direction. The Lorentz force is what makes our electric motors work. Without this force, our modern world would be quite different.
EMF, or electromotive force, refers to the voltage created by a battery or by a changing magnetic field. Counter EMF, also called back EMF, is a related phenomenon that we will illustrate in this animation. Here is a simple circuit featuring a battery, a knife switch, and a light bulb. This circuit also contains a wire coil that serves as an inductor. Inductors store energy in the form of magnetic fields that are generated around them when a current passes through them. They are called inductors because they induce a voltage in their coils when that magnetic field changes. We will see this in a minute. The elements in this animation are not represented to scale, and the action we will show in super slow motion actually takes place in the blink of an eye. But this animation is helpful for illustrating how back EMF works. When we power this circuit, the electrons in the current create a magnetic field around the wire as they move through it, as shown by these blue arrows. If the wire is formed into a coil, like this inductor, the magnetic field lines converge in the center. They gradually build up to a maximum magnetic field that is much stronger than the one around the straight length of the wire. Let's watch this again, but this time we'll pay closer attention to what's happening in the wire conductor. In this parallel circuit, the current can travel either through the inductor or through the light bulb. When the current reaches this junction, it splits and flows to both the inductor and to the light bulb. At first, the current flows much more strongly towards the light bulb. This happens because as the magnetic field in the inductor grows, it induces its own voltage through Faraday's law. This is called electromagnetic induction. So the inductor here is creating a back EMF represented by this yellow arrow. Back EMF always opposes the change that created it. So in this instance, the back EMF is opposing the change created by turning on the circuit. It opposes the current. The result, as you can see, is that the back EMF effectively diverts the current away from the inductor and toward the light bulb. This causes the bulb to light up, but only briefly. Once the magnetic field around the inductor reaches its maximum field, the back EMF fades, and the current now favors the path through the inductor because the bulb creates some resistance to the current. The same phenomenon occurs when the magnetic field is shrinking, which happens when we open the switch and stop current flow from the battery. Once again, the back EMF opposes the change that created it. In this case, the change is the cessation of current. So, opposing this change, the back EMF wants to maintain the current, which flows once again to the bulb, causing it to flash before it fades away altogether. Electromagnetism can be a complicated subject, but luckily you can find two of the most useful tools for understanding it right at the end of your arms. Your hands. They help you to write letters, type on a computer, and throw a frisbee. They also help you understand two concepts of electromagnetism. We will use this battery and wire to create a current so that we can illustrate these concepts. While electrons actually run from negative to positive, the convention is to think of electricity going from positive to negative, so that's how we show it here. When current flows through a wire, it generates a small magnetic field around the wire, as shown by these blue lines. If you hold your right hand like so, with your thumb pointing in the direction of the electric current, then the curl of your fingers will show the direction of the magnetic field. This is known as the right hand rule. We need to reverse the direction of the current to illustrate the other concept. We also need a magnetic field to explain what's happening. These two magnets provide that field, depicted here by the blue lines. When charged particles enter a magnetic field, the field exerts a force on them. You can use your hands to find out the direction of that force. Position your left hand like so, with your index finger pointing in the direction of the magnetic field, your middle finger pointing in the direction of the current, and your thumb pointing up, forming a right angle with your index finger. Your thumb shows the direction of the force, called the Lorentz Force, exerted on the charged particles. This is known as the left hand rule. The right and left hand rules are two handy ways of better understanding the interplay between electric currents and magnetic fields.
Showing how a magnetic field affects the charged particles in a plasma arc. Here I just placed one of the electrodes in the center of a ring magnet with 12,000 volts applied across the gap.